Welcome back to another video. So in this video we're continuing with another measure theory related problem. So like in the previous video I made, we're given a measure space with the total measure of the space equal to 1. And the first thing we want to show is that the LP spaces are basically descending. So if you have a smaller value R and then a larger value S, then this containment happens, so the LP spaces keep getting smaller. And then we want to figure out which conditions on the space X make these equal to each other. So we know that L, R, of mu. So the first thing we're trying to show is that this contains ls of mu, but we want to know under which conditions is the reverse containment also. When does this also necessarily hold? Okay, and these are both things that really only apply when the space has finite measure. So you get this nice containment when the measure is equal to 1, for example, but if the measure was infinity, this wouldn't be true. And there's simple examples of that. So this first containment is actually immediate from something that I proved in the last video, which is that if you have a measurable function f, its r norm is less than or equal to its s norm whenever r is less than s. And, you know, again, this was proven in the last video that I made that I'll give a link to. But so if f is an element of ls, then this second value is finite by definition. And so then this inequality forces the r norm of f to also be finite so that f is in LR as well. So this is actually immediate as long as you know that this inequality right here is true. So that's kind of like the easy part. So the second part that's a lot harder is when are the spaces equal? So when is it necessarily true that LR is contained inside of LS in addition to the reverse containment being true? And that's basically a lot harder. So you can take some time for yourself to think about it if you want. But it turns out that this is equivalent to the condition that, so again, we're still assuming that the measure of x is equal to 1. But so if x doesn't contain sets of arbitrarily small positive measure. So you think about, there's measure spaces like the interval from 0 to 1 with Lebesgue measure. That's clearly an example of a measure space that, that does contain sets of arbitrarily small positive measure because it contains intervals, and you can make the intervals as small as you want. But if x doesn't have that property, then that's actually equivalent to the property that LR is contained in LS whenever R is less than S. So we can prove this. One direction is slightly different from the other direction. So the first thing we can do is we can assume that this property right here holds. So we can assume that X doesn't contain sets with arbitrarily small positive measure. So that means that there exists a positive epsilon, say, and given a subset E of X, if the measure of E is less than epsilon, then this forces the measure of E to be 0. So that's what this condition is saying. And we want to use this to prove that this containment right here happens. So let's say that we're given a function f that is contained in LR. So that means that f is a measurable function on x, and the r norm of f is not infinity. And our goal is basically just to show that the s norm of f, is also finite. And to do that, we need an inequality, which is Chebyshev's inequality. So you always need some kind of inequality. It's just a question of which one you basically need. So this says that the measure of the points such that this inequality holds. So the measure of this set for a positive m is less than or equal to 1 over m to the r times the r norm of f. And we know that this is not equal to infinity. So this is just a finite value here. And what we can observe is that as m goes to infinity, the right side of this goes to 0 because of that. So that actually means that, basically what we're doing is we're measuring pre-images, right? So we're measuring like f inverse of m infinity, something like that. I guess it's absolute f inverse. And so we're saying that the measure of these sets goes to 0 as m goes to infinity, basically. So why is that useful? Well, again, our space doesn't contain sets of arbitrarily small measure unless the measure of the set is 0. So that means that there exists m0 positive such that the measure of, so the set of points basically for which f is at least m0, the measure of this is equal to 0, right? Because the measures of these sets keep getting smaller and smaller and smaller, and so eventually they're forced to be equal to 0. And so for some m0, this is true. So what that basically means is that f is actually bounded almost everywhere. Right, so almost everywhere we have that absolute f of x is less than or equal to m0. So if you think about what this means, now thinking about the s norm of f, so that's really just this integral, and then to the 1 over s. The 1 over s doesn't really matter right now. And if you think about it, this is just equal to the integral over e of absolute f to the s, to the 1 over s, where e is absolute f inverse of, what would it be? 0 to m naught, right? So if you try to integrate f over the entire space, you might as well just integrate over the set of points for which f is bounded by m0, because the complement of that set has measure 0 anyway. Okay, but this integral is clearly finite, right? Because the measure of x is equal to 1, so the measure of e is less than or equal to 1. And so the integral of absolute f to the s over e would be no more than, again, f is bounded by m naught, so this is no more than m naught to the s, just m naught to the s, which is finite. Okay, so we took a function f that we assumed was R integrable, so we assumed that it was in LR, and then we just showed that its s integral is also finite. Therefore, it is contained in LS. And so this shows that the containment that we were trying to prove, that this is true. So that's good. So now we want to somehow prove that there's an equivalence, right? So we just showed that if x has the condition that, x does not contain blah, 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 sets of arbitrarily small positive measure, then it's always true that this containment holds. So one thing that we could do to show that they're actually equivalent now is we could assume that x doesn't have this property. So we could assume that x does have sets of arbitrarily small positive measure. And then we could show that this containment, in that case, doesn't hold. So let's try to do that. So now let's assume that x does contain sets of positive measure, and you can make the measure as small as you want, basically. And we want to use a trick, right? So you want to kind of think about like functions like 1 over x. So if you think about the function 1 over x on 0 to 1, how this function really works and why it's integral, right? So why this integral is infinity is basically because there's sets of smaller and smaller measure, right? So like you have like this interval, this interval, this interval, and you have like smaller and smaller intervals, and the function gets bigger and bigger at an appropriately fast speed on those intervals. And so we want to construct a similar function in this case, and we want it to have a finite R norm, but not have a finite S norm. And that will show that this containment doesn't hold. So that is basically the idea. And we know that we can find a subset of x where, for example, the measure is no bigger than 1/3. So we know by assumption that we can do that. And then we know that we can find another set whose measure is no more than 1/3 the measure of the original set. And so on, right? We can keep recursively finding sets where the measure of En is no more than 1/3 the measure of En minus 1. It'll make more sense why I'm choosing 1/3 in a second. But basically the point of this is that we can get an infinite family of sets like this. And their measures certainly go to 0. So that's nice. But what's more, we can observe what happens if we take En and we subtract the union of all the following sets. Right, so if we take En and then we subtract all the EKs for k larger than n, what happens is that this is always non-empty. And not only is it non-empty, it actually has positive measure. Okay. To see why that's true, observe that, so if you think about the measure of EK, so it might be easiest to think about like E3, right? The measure of E3 is no more than 1/3 the measure of E2. But then if you recursively go one more step, this is no more than 1/9 the measure of E1, right? And so in general, basically the measure of En plus k is going to be no more than, if you just keep applying the inequality over and over, you'll get 1/3 to the k measure of En, right? So you have this kind of bound. And so that means that if you think about like what is the measure of the union, and k goes from n plus 1 to infinity of ek, so what is the measure of this? Well, it's no more than the sum starting at n plus 1 of these measures. Right. Oh yeah, what I wrote here doesn't perfectly match here, but you can see that this each of these measures, so this is no more than 1/3 measure of En, okay, plus 1/9 measure of En, plus dot dot dot, right? And because the series 1/3 plus 1/9 plus dot 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 converges to something less than 1, this is no bigger than, this is smaller than the measure of En. Right? So the point of this is that by construction, we took En and we subtracted off a set, but the measure of that set is strictly less than the measure of En. And so the resulting set that you get, right? So if you define like Fn to be En minus the union of all of the EKs, this forces the measure of Fn to be bigger than 0 still. Okay. So why did we do all of this? Well, we basically now have a family of sets. We have a chain of sets F1, F2, F3, dot, dot, dot. By construction, you get each of the Fn by subtracting off unions of sets. And so the Fn are pairwise disjoint from each other. So the Fn are all pairwise disjoint from each other, and they all have positive measure. So now what we can do is we can define a function, which we'll call f of x, and this will be the sum over n greater than or equal to 1. And what will we do? We'll take mu of Fn to the negative 1 over s, and we'll just multiply it by the characteristic function of Fn. Okay. Great. So one thing that you'll immediately notice, and this will help it make more sense why we define it this way, is what is the integral over x of absolute f to the s power, right? So what is this equal to? And by the way that we defined f of x, you can see that if I take f of x and I raise it to the s power, I just get mu of Fn to the negative 1 times chi of Fn. And so if I'm integrating, what I'm basically getting is I'm getting this integral, but I'm integrating over each of the sets Fn. And so on each of the sets Fn, I'm just multiplying by the measure of that set. So the integral would be, you would integrate over F1, integrate over F2, integrate over F3, and keep doing that. And on each of those sets, f to the s is equal to this. And then you would multiply by the measure of the Fn. But this is just the sum of 1 plus 1 plus 1 plus 1 plus 1, so this is infinity. So this function, clearly is not s integrable, right? So f doesn't belong to ls, doesn't belong to ls, but it does belong to lr. So if you think about raising f to the r power and integrating that instead, here you would get mu of Fn, and what would you have? You would have to the negative r over s, and then times mu of Fn, right? So this is the integral of absolute f to the r. So another way to write this is that you're adding n greater than or equal to 1, and you have mu of Fn to the 1 minus r over s. And going way back to the beginning of what we decided r and s were, we know that r is less than s, and so r over s is no bigger than 1. And so that tells us that mu of Fn to this power is no larger than 1 over 3 to the n to the power of 1 minus r over s. Again, recalling that the Fn were constructed so that they all have measure no larger than 1 over 3 to the n. Okay, but so then if you think about the geometric series, if you think about the sum of basically these values for n greater than or equal to 1, another way to write this is like this to the n power. And you can see that the common difference here is less than 1, and so this is definitely less than infinity. So this f function that we constructed, right, it basically has, you know, on one of the fn sets, it has a fixed value, and then on another one, it has a fixed value, and then so on. So it's kind of hard to visualize, but it would, quote unquote, look something like this. So this f has a finite r norm, but it doesn't have a finite s norm. And so that means that LR is not contained in LS. So yeah, that's a rather hard problem, in my opinion, but that's it.